Okay, welcome to Robotics 2. In today's class, we will continue the discussion on the problem that we started in last class, and we will talk about the trimming and linearization. So recognize in the last class, we started with this problem. We have a spring, we have a mass. This is the spring, this is the mass, and this spring is nonlinear. The differential equation of motion is mx double dot plus kx plus kx cube is equal to u. And our objective is to find out a linearized equation that can approximate the behavior of the system. So this linearization should give us a model in state space. It can give us model in transfer function format. So in the last class, I kind of went through the process and discussed how the linearization is done. I'm gonna go through that process one more time today and perform first trimming, then linearization, and then comparison with nonlinear system. Because please understand, the purpose of linearization is to come up with a simpler equation. But these simple equations should reflect the dynamics of the original system, which means the linear equation that you have, say x dot is equal to ax plus bu. This equation should capture the dynamics of this nonlinear system at some operating point, at certain operating point. If it does not, then clearly this linearization is of no use. So what I'm going to do is, I'm going to continue with what we started in last class. I'm going to go to Matlab, and just to tell you, this linearization can be done multiple ways. The linearization can be done inside Simulink using linear system toolbox. And that's what we talked about in last class. The linearization can be done on command line using the function Lin Mode. And I will demonstrate these two techniques today. Later, we will look at the project 4 equations. So once we understand, we will look at project 4, and I will show you how to perform the trimming and linearization for Aerosonde UAV. And please note, my results are going to be different than your results because the parameters or UAV design parameters are different, but technique will be the same. And this trimming is performed using something called as sequential quadratic programming optimization technique. So it's a numerical technique. So sometimes there is some trial and error that is needed so that we get good results. Also, one thing in the passing, I would like to tell you that uh, I'm gonna teach you sometime in this, not today's class, but sometime this semester, interface with an actual flight simulator. So you can use, and I was trying to do that, and I would like to show you the integration with joystick, with joystick, also called as flight stick. So if you have an Xbox flight stick or Xbox joystick, or for that matter, uh, uh, Kinect joystick, or if you have Nintendo Switch joystick that can work with PC, so you can actually look at a flight stick, joystick, something like that, that can talk wirelessly or in a wired fashion with the PC. Or you can have something like a joystick with a D-pad and some buttons that can connected via USB or Bluetooth to PC. That will work. No, laptop keypad will not work. For to have like to interface keypad or keyboard, what you, so say for example you have a keyboard, then you will have to write a Matlab code or something called as Matlab driver that will take keyboard commands and interpret it into the joystick commands and then feed that to your Matlab Simulink code. I tried mapping that. It's not trivial. So that the writing the driver code that will take the keyboard input and map it to joystick input is not easy. So, and I was looking at the joystick. These joysticks are available on eBay for a couple of dollars. If you buy it from Amazon or Walmart, they are about $3 to $4. You can buy two joysticks for $10. So I don't think they are expensive, but it's a good exercise. And then finally, once we integrate it, the flight sim, you can actually fly your aircraft inside the flight sim environment, maybe over Honolulu, or maybe over India, or maybe over Bangladesh, or Pakistan, or Europe, or Paris. So that would be a fun exercise to perform. So I would encourage you to get it, but it is not required. We can work without the joystick input as well. Okay, any question before I go to Matlab? So I'm gonna share my screen. And now you should be able to see my Matlab window. And there's a joystick simulation on the side. We'll ignore that for a minute. So your chat is visible to me, to everyone. So don't use private chat. And if you have any questions, you can raise your hands or raise your hand, or you can type the question in the chat window. So first and foremost, what I'm going to do is I am going to look at, say, example linearization. So, and to be honest with you, we will reconstruct this code from the scratch. So, and this is just a sample solution. I just want to have it as a reference in case if I make mistakes, because I found out that sometimes if the old variable is still in the memory, then the simulation will not work. So I'm going to start with the new simulation, and let's start with this guy. And this is the same equation. This is the same equation that we worked in last class. So I just want to make sure that you have this Simulink file. And I'm going to make few changes to the Simulink file so that it looks like what we had the last class. And so step one, go to library browser and create an input. Go to library browser and create an input. Now I just want to make sure that you are you have this Simulink code inside your prompt. If you look at the Matlab function, this is the same Matlab function that we used in last class. It's the exact same Matlab function. Now, what I'm going to do is, so couple of things. I'm going to delete the superficial let me delete this so that we can start from the scratch. So there is no input or no output mapped at this point. So this is the blank simulation, and let's see if this works. And this should be working. You should get a flat line because the initial conditions here are 0. I'm going to change my initial conditions to 1, 0. And I will run this. And now you should have this plot in front of you. Any questions at this point? Yeah. So integrator, initial conditions. Okay. Now what I want to do is I want to perform the trimming. So what I'm going to do is I'm going to change the initial conditions to 0, 0. So what I want to do is, this is important. I want to trim at the initial condition 0, 0. In other words, I would like to find out the equilibrium solution for this system. So check this out. So I'm going to go to apps. I'm going to go to model linearizer. In the tolerance, yeah. So to answer Jade's question, I'm changing deliberately the initial conditions to 0, 0 because I want to trim the system at the 0, 0 initial condition so that I can compare apples to apples. So I want everyone to change the initial conditions to 0, 0 back again. So now what I want you to do is I want you to go to model linearizer. Once you go to model linearizer, first and foremost, you can come up here, model initial IO, then model initial conditions. I'm gonna trim the model. I'm going to trim the model. So click on trim the model. And when you trim the model, you have states, you have input, you have output. State, input, output. Now please try to understand there are two outputs, 1 and 2. There is one input over here. So what I'm going to do is I'm going to trim the system when the derivatives are 0, which means state 1 is going to be in steady state, which means derivative is equal to 0. State 2 is going to be in steady state, which means derivative is equal to 0. Now, input and output relationship that needs to be found out. So what I'm going to do is I'm going to start trimming. And then when I trim, you will see that the model got trimmed successfully. And please note that at trimming at initial state, everything is at 0. Everything is at 0. That's totally fine. Now, in next step, what I want to do is I want to go to result viewer and I want to go and linearize this system. I want to go and linearize this system. To see the linearization, go to step. If you click here, you can perform the linearization and you can generate the plots. But what you want to do is I'm just gonna linearize with no plot. So basically, then if you run the linearization, it will give you an error. And the reason for this error is we haven't marked input and output for the linearization. So this is the way you would do it. So right click on the input, go all the way to linear analysis points, and then go to input perturbation. Okay, let me see. Okay, go to input perturbations. Then go on to the output, right click, linear analysis point, and then you can click on output measurement. Right click, linear analysis point, and then output measurement. So now the Matlab system knows, and I will make it a little bit bigger. Now the Matlab knows that we have this as input, arrow going down, and these two are outputs. So I'm going to close this and try to rerun my linearization again. And now when I linearize, what I have is I have this system. And this is fantastic. And I'm going to wait here for a second and make sure that everyone got this result. This is the linearized equation for our system. Now, the story does not end here. The linear option, you should have the linear system toolbox. So that will show over here. You can trim before or you can trim after. To answer Zubir's question does not matter. But before linearization, you need to specify the input and the output. Okay. At this point, everyone got this linearization result. I just want to make sure that the file you gave us has output measurement on integer. Okay, you can try that, but I want to have measurement over here to explain few points. And I'll tell you what I want to talk about. Just a second. Bear with me, Borna. Now, let's again recap. There is one input. There are two outputs. So you need to click on the result viewer. Can I right click in the options? So you need to click on model linearizer. That will open. You have to go to model input output. You have to select the operating point OP trim. Then you will get the trim solution. And then you have to click here. And then you will see the linearization without plot. So model linearizer would go here. So simulation, debug, modeling, format, and app. This is where you will find the model linearizer. Okay. Now what I want to do is, I want you to go all the way to linearization result here. And can you see it shows the display linearization in state space? Drop this menu and there is a transfer function. And now this will give you the linearization as a transfer function. So by dropping this menu, you can get the linearization in the state space form, and you can get the linearization in transfer function form. Now what I'm going to do is, I'm going to try to compare the performance. So I'm going to simulate the transfer function, and I'm going to simulate the state space. So result viewer and rerun your code. Just rerun, Subir, then you will see. So go to continuous and grab state space block in your window. So grab the state space block in your window. And now what I'm going to do is, I'm going to double click in the state space block and input A matrix, B vector, C matrix, and D vector. So double click. My A matrix is 0, 1, 0, 1. So -1, 0. And I will keep this here for a minute. My B is 0, 1. My C is 1, 0, 0, 1. My D is 0, 0. So what I want you to do is, I want you to drag and drop the state space block from continuous. Double click on this and then enter the state space linearization that we got. 0, 1, -1, 0, 0, 1 as B. C matrix is 1, 0, 0, 1, and D matrix is 0, 0. Now click OK. Now what I'm going to do is, I'm going to add a scope plot over here. I'm going to add a scope plot over here. Now what I'm going to do is, I'm going to add a simple source, maybe simple sine function or a simple ramp function. It's totally up to you, does not matter. So I will add a sine wave here. And what I'm gonna do is, just to make it a little fancy, go to signal routing, and signal routing is here. There's a manual switch. I'm gonna add this manual switch, delete, add it over here, add it over here, and then add it to U. Double click. So now I can disconnect the old input and I connect the sine function. Now to double click on sine wave, please understand this is a linearized solution or linearized system. So it needs to be close to the equilibrium point. So that's why I'm going to decrease the amplitude to 0.1. So please note the amplitude is decreased. So double click on the sine wave, click on the amplitude, change it to 0.1. And go to simulation and then run the simulation. And you will notice there is first scope and there is this second scope. So the top scope, this scope came from the actual nonlinear system, and this bottom scope came from the linearized system. Top scope came from the nonlinear system, and the bottom scope came from the linearized system, nonlinear, linear. And you would notice that they are pretty close, which means our linearized approximation works quite well for the nonlinear system. Now I want to continue this discussion further, and I want to go back. I want to go back to the linearization result and go to linearization result, change it to transfer function. Now here, please pay attention. There are two transfer functions. Why there are two transfer functions? Because transfer function is the ratio of output divided by input. And for transfer function, it has to be one output and one input, one output and one input. Our input is U1, but I have two outputs. This is my Y1, this is my Y2. So Matlab gave me two transfer functions. One is the transfer function between U1 and Y1. And I have another transfer function between U1 and Y2. Now what I'm going to do is I'm going to use these transfer functions and try to get the same result. So if you go to continuous, there is this transfer function. I will again add one more transfer function. So the first transfer function will be the relationship between U1 and Y1. U1 is this input. So this is the relationship between U1 and Y1. And second transfer function is the relationship between U1 and Y2. So I'm gonna drag this over here. Now let's program the transfer function. So the numerator coefficients are, please note, the denominator starts with s square, s to the power 0 and s to the power 1. So I have 1, 0, 1. And then the transfer function is 1. So if you expand, you should be seeing the same transfer function as the first transfer function here. This transfer function should look like exactly the same transfer function here. Now for the second transfer function, you need to make following changes. The denominator would be 1, 0, 1. And the numerator is going to be 1, 0. Now, once you do that and expand, now notice that your second transfer function would look something similar to this. For comparison, I'm going to go back to library browser and I'm going to use the scope and then connect these two outputs to the scope. So now I want to show you what we have. This is the nonlinear system. This is the nonlinear system. Nonlinear. This is the state space representation. And this is a transfer function representation. So what you have is you have three different methods: nonlinear, linear state space, and transfer function. And what I'm going to do is I'm going to run them simultaneously. And I'm going to click on the first plot. This comes from the nonlinear system. Second plot, this is the state space representation of the nonlinear system. And the third plot, which is the transfer function representation of the nonlinear system. And please observe that these three plots are exactly the same. What you need to do, so look at this. We had a nonlinear system. We performed the linearization. We actually got the linearization in the state space. We got the linearization in transfer function, and it gave me the exact same result. Any questions at this point? Well, I want to point out few things. Transfer function is one-to-one relationship. There is only one output, one input, one output, one input. But the state space can be one input or multiple outputs, multiple inputs, multiple outputs, multiple output inputs, single output. So state space can handle CISO systems, single input, single output systems, MIMO systems, multiple input, multiple output system, but transfer functions are used for single input and single output. So Ghazi, for state space, you have to go to continuous, and then here is the transfer function. No, it basically, it's totally depends on the type of control you are going to design. If you can design the control in state space, like pole placement, or you can design the control in transfer function, and we will look at both. It completely depends upon the application and the type of system you are planning to control. Okay, at this point, I just want to make sure that everyone understood what we did here. And I'm sorry I did not go back and forth, because I'll tell you what happens if you go back and forth. If you go back and forth, one plot, two inputs in the scope. Yeah, because the scope is grabbing output from first equation and output from second equation. So this is the plot of output. If you want input versus output plot, then you need to create XY plot. So if you want to, so XY plot is sync. So you need to create XY graph. So where you connect something like this, you connect X, and then you connect Y, and then run. So then you will have issues with multiplexing, because now, so you should do something like this. So check this out. And that will give you sort of representation, phase plane representation. And then you can actually generate the XY plot. So right now what we are doing is we are just generating the output plots. I use the manual switch just to give you some functionality update. But that manual switch, once you do the linearization, we are not going to use this system. But here is something I want you to try. This trimming or linearization is about initial conditions 0, 0. My question to you is, if I change these initial conditions, would my linearization work? So for an example, I'm going to change my initial condition, and this is a very important question. Please understand. I'm going to change my initial condition and see if my linearization works. And once again, I'm going to try. So let me run, and run. You will see the result is completely different, because right now the system that we have created, this linearization, is about 0, 0. But our system actually is not at 0, 0. This is at 10, 0. So what that means is I need to linearize this again. So flip the manual switch. Then you have input, you have output. Go back to the app, model linearizer, then model input output, then linearize trim model, and then you have to repeat through the trimming process. So your states are 0, you can 0, 0, your input, output. You will have to perform this linearization again, and then you have to trim again, and then get a new system. But now, so this is something that happens, and I was trying to avoid this. So this will give you an error. The Simulink model is out of sync with your operating point specifications. And this is what happened in the last class, because now we have changed our initial positions. So you need to sync with the model, and then start trimming. And once you do the trimming, again, actually initialize, you will have to reinitialize and perform this process again. But what I'm trying to say here, and I think most of you understood, that I will have to repeat this process from the scratch, say if I change my initial conditions. Now, the last thing which I want to talk about is how to perform the same thing using Lin Mode. And this is interesting. So I'm now gonna, let me delete this. I'm gonna delete this all. And I'm gonna connect this guy here. And this is important. And I'm gonna save this simulation, save as trial 1, or I'm gonna call this T1. Okay, I'm gonna save this simulation as T1. So this entire simulation with 1 input, 2 outputs, it's saved as T1. Before I go any further, I just want to make sure that everyone has this clean model. Now run this model. And as you can see, this model runs, but it is running at the initial condition 10, 0. Let's change this initial condition again to 0, 0. Run. Now you see that there is nothing, no output. Now I'm going to go to command window. So I will show you both. So I have this Simulink file and I am working at the command window. This is my Simulink file and I'm working at the command window. Now I'm going to use, so to answer Zubir's question, you have to sync with the model. Only then the initial conditions will get updated or Matlab would complain. Now, what I'm going to do is I'm going to use something called as the Lin Mode. So everyone, please pay attention. The command is sout is equal to Lin Mode in the parentheses the name of the Simulink file. Everyone, pay attention. Sout, copy. I'll put this in the chat window. Make sure your Simulink file is saved as T1. Enter. Now, once you enter, the Matlab has done the linearization and gave you a struct or a structure. That structure has A, B, C, and D. Once again, it has A, B, C, and D. Those are your A, B, C, and D matrices. Before I go any further, everyone got this S out? Did you get S out? Do you see the output the way I see the output? Okay, the next part is super duper important. Yours is 8 by 8. Ah, I know, Borna, you did not modify the baseline Simulink model like this. Your Simulink model has floating SS and TF. All right. Second call. Everyone got this struct with A, B, C, and D? Okay. Yep. Time to go back and clean it up. Travis, you need to clean up your model. And then you have to save that file as T1. And that file t1.slx should be in your working folder. So can you see this working folder? Travis, you should be able to see t1.slx in your working folder. And your t1.slx should have the exact same structure. All right. Now, next part is super duper important. Everyone pay attention. I want to find out the value of A. A is equal to sout dot A. Enter. And your A matrix, do you remember we had the exact same A matrix when we did the linearization using the linear advisor or linearizer. Next, B is equal to sout dot B. C sout dot C. D is equal to sout dot B. So now we have done the linearization using Lin Mode. So I showed you two ways of doing linearization. You can use the linear analysis tool, or you can use the Lin Mode and then perform the linearization. Now, the next part is very important. And before I go and enter those commands, I just want to make sure that everyone got these A, B, C, and D. Okay, chat window, give me some feedback. Did you get this A, B, C, and D's? Got A, B, C, D's? Yes, but I would recommend you look at the Matlab help on comparison between Lin Mode and linear analyzer. Lin Mode has some limitations that okay. So Ghazi, maybe during the office hours I can explain this once again, but there's some part I need to finish real quick. Now I need to use the Lin Mode and construct the transfer function. It is not straightforward. So for that, I need to do is, this is the command num comma den is equal to state space to transfer function a comma b comma c comma d. And once you enter, this is what you get. However, if you recognize, earlier we had two transfer functions, and now this gives me a little bit complicated equation. The numerator of the transfer function is not one, but it's two rows. So what this is doing, since I have two outputs, look here, I have this output and I have this output. The transfer function corresponding to this output that I highlighted is this numerator. This numerator corresponds to number 1. This numerator corresponds to number 2. So now I'm going to get the transfer functions. So check this out. Transfer function num first row all columns, no, all rows, no, all rows. So I need the first row all, first row all columns. Then that gives me the first transfer function, and second row. So second row of the numerator and denominator gives me the second transfer function. So this is your TF1, and this is your other transfer function. So everyone understood how to get the state space representation and transfer function using Lin Mode? I'm looking at the chat window, and I'm looking at I don't see any raised hands. So everyone clear on this? Okay. Now we use the equilibrium point. So I would encourage you to look at the help Lin Mode, and then actually Lin Mode has a lot of options that we did not discuss. You can specify operating points, trim conditions, and linearization. But I would encourage you to study Lin Mode a little bit, because that you will use for your project. Now I'm going to show you how you would use this technique for your project. Can I move on to the project 4, or any questions here? This exercise is super important. So now I want you to go to derivatives 1 sim SLX. And understand that I emailed this file to you the other day, I think on yesterday. So please use this file. However, there is something I want to mention, and you want to be careful. So in this code, when you go to simulation, go to modeling. So first and foremost, does everyone have this Simulink file in front of you? Okay, now I'm gonna give you some little bit explanation. So this is the elevator, aileron, rudder, and throttle. Elevator, aileron, rudder, and throttle. This is the wind model. We are neglecting the wind gust and wind. So all these constants are very small values. So we are neglecting those values. Now, if you look at the project, and please note, this is for Aerosonde. So your solution is going to be different. So first and foremost, I want to go to this force moment 4. If you double click, look at the output of this force. You have force 1, force 2, force 3, torque 1, torque 2, torque 3. You have the airspeed, VA. This is super important. Airspeed is the 7th quantity. Airspeed is super important. Alpha is important, and beta is important. Now, I want you to track that with the outputs that I have identified here. The first output I tap is the VA, which is the airspeed. Second output, so first output, the third output here, the second output that I tap is alpha, and the third output that I tap is beta. So this is airspeed, alpha, and beta. So if your Simulink file is completely different, then what you should do is, and this is nothing different, this is exactly the same file that we worked on in project 3. So Ghazi, you have some issues with your email. That's why you are not getting my email. So I suggest you go to announcements and download project 4 discussions. It's on Canvas. Thank you, Jay. Now these are the inputs, and please note I have already marked the inputs here. So, and I have already marked the outputs here. So that makes it easier for trimming. But here is something I want to show you. Go to model settings, and if you do, and I want you to look at data import and export, and unclick input and initial state. Unclick input and initial state. So please make sure that these two are not clicked. Otherwise, your simulation will not run. Okay. Once again, go to modeling, simulation debug modeling, click on model settings, and go to data import export, and then uncheck load input and initial state. Click OK. It's always a good idea to see if your baseline simulation is running. can I copy the line I changed? I did not change any line. The MATLAB code. This is the MATLAB code. I didn't change anything. No change in the MATLAB line. So I'm trying to. So go to the Simulink file and try to run this. Your code should run. If your code does not run, that means you have some baseline variables in the workspace that are not available. Yes, it's project 4 discussions RAR. So your baseline code should be running. Is your baseline code with this change running? If your code is not running, then only reason for that code to not run is you go to modeling, go to model settings, and your MATLAB is trying to access the variables that are not in the workspace. So unclick input and initial state. Okay. Okay, next part is super duper important. So I'm going to take a minute just to make sure that everyone has this code in front of them running. And just tell me if your code is running or not. Of course, go to modeling, go to model settings. Yeah, plane will do some crazy things. Don't worry about the plane. Okay, one more minute. So go to simulation, run this code, make sure that you get something. It should not give you an error. Your code should be running. Plane can do some crazy things, or it can just stay stationary, doesn't matter. But you should see the bar here that the code is running. Yeah, bar is slower than 10 seconds. That's totally fine. Because right now it's using its ODE stuff and all. So we will do some real-time simulation matching later. But as long as your code is running, that is important. Yeah, of course. So UAV parameters, they should be in the MATLAB window. So here, your UAV parameters should be here. All right. So I'm going to show you the next part that is super duper important. So everyone, please pay attention for a second. Now, what I want to do is, I want to take a minute and read the trim conditions that are specified in the problem. So what I'm going to do is, I'm going to go back to the problem statement. This would be a good time to open the textbook or just open the project 4 description. So I'm going to go through the description step by step. So the first 5.1 is make yourself familiar with trim and Lin Mode. Second part is copy and rename your current Simulink diagram to trim. So this is the diagram that you should be using. The only difference is your UAV parameters will be corresponding to your Zagi plane, and then Zagi plane does not have rudder. Zagi plane only has elevons. So you will have to perform the mapping in your code to map elevons to elevator and ailerons. So that mapping is given in the textbook. In case if you are wondering where that mapping is given, I discussed that in the class, but I will also tell you the page number where the mapping is given. Page 43. Elevon mapping to elevator and aileron for Saudi. Okay. Now, what I want you to let's start with the trimming exercise. So there are three outputs for trimming. So first output that we need to trim is the airspeed, VA. So this is the airspeed. Then there is angle of attack, and then there is beta. So what I'm going to do is I'm going to perform the trimming using the Simulink app. So I'm going to go to app. Go to model linearizer. So what you should be seeing is the model linearizer in front of you. Everyone got model linearizer? Then analysis, model input output. Please note we already have the inputs and outputs mapped. I can just do result viewer. I drop down, go to operating point, trim model, click, and then you will have these different states shown to you. It does not, please notice, it is similar to the one problem that we solved earlier, but earlier problem was simple. Now please note, derivatives one sim integrator, this tells you these are the conditions here, which means these are mapped one-on-one to the derivatives function. So if you look at these conditions, and I'm going to show you what they are. State 1 is Pn, state 2 is Pe, state 3 is Pd, U is state 4, V is state 5, W is state 6. Then P, theta, psi, and then you have P, Q, R. So these 12 states are these 12 states. So these are the 12 states. Now the first and foremost important question here is, what states are known and what states are unknown? And out of these, which states are in steady state and which states are transient? So one thing I have to clarify here. When I say steady state, which means the derivative of state 1 is 0. Derivative of state 2 is 0. Derivative of state 3 is 0, and so on. So when this steady state is clicked, that means the derivative of all the states is 0. That is not right. So at this point, I want you to think a minute and tell me what derivatives should be 0. Which states should be 0? And some hints are provided in appendix F. If you go to appendix F, clearly, the first derivative we don't have to worry about. The second derivative we don't have to worry about. The third derivative, again, that has some specification. So third derivative has some specification. So I will unclick this. But then fourth, fifth, sixth, seventh, eighth. Fourth, fifth, sixth, seventh, eighth. These derivatives are 0. 8 derivatives is non-zero. 9, 10, 11, 12. So these derivatives are 0. So I want you to focus on these steady states. And notice the first derivative we are not concerned. Second derivative we are not concerned. So it would be instructive to go to page 278, appendix F of textbook. And I will give you a minute if you have your textbook with you, or if you can look at the problem statement. The next part is because the aircraft is in level flight. So aircraft is going in the steady level flight. That's why the derivatives. So what this tells me is an aircraft can go fast in X direction, can go fast in Y direction, can go fast in Z direction. The one thing that I want to specify here is I want this third state to be, maybe I want my aircraft to fly at say 1000 meters altitude. So the Z value, the height is 1000. Then I'm gonna go to the next part is state 4. State 4 is actually the forward speed. And when the pitch angle is 0, the forward speed is equal to airspeed. And I'm gonna say my airspeed is equal to 25. So my airspeed is 25. State 4 is 25 because this is the U. Okay, Zubir, if you want to try first 3 terms are 0, you can try first 3 terms 0 and we'll see what happens. Just bear with me for a second. Now the next part is go to outputs, and I want my first output, which is the airspeed, to be 25. Then my angle of attack, you can specify the angle of attack or it doesn't have to be specified, but my side slip, I'm going to specify to be 0. So these are, and I'm going to say I'm going to start with the full throttle. So I'm going to say I'm going to start with 1. So these are the states. And please understand, this is a numerical optimization technique. So we may have to go back and tweak some of these parameters to get some trim solution. But this is something we are going to start with. So airspeed 25, side slip 0, and I'm going to start trimming. And then you will see that it started solution. It may give a trim point, and so now can you see that it gave me a trim point? And I'm going to click on this trim point, and I'm going to investigate how does this trim solution look like. Now, to answer Zubir's question, Zubir, I want you to take a look at the first state. Look at the value of the state. So this state is 0. This state is 0. The third state is 1000. There are some non-zero derivatives, but that's okay. State 4, which is the forward speed, is 25, and all other states have some non-zero values. But my derivatives are fairly close to zero. My derivatives are fairly close to zero. Now I'm going to go to input, and I will see that my elevator deflection is minus 0.129. My aileron deflection is almost zero. My rudder deflection is almost zero. And my thrust is 1.15. Then for output, you will notice my side slip angle is zero. My airspeed is 25, but my angle of attack is non-zero value. Just a second, Zubir, I'll answer your question. Just a second. But before I go to the question, I just want to make sure you run this and you get some values here. Now, if you look at X3 is the displacement, or it's the altitude. If I state my altitude is zero, your aircraft will not be seen in your simulation, because if you look at your simulation is somewhere from minus 5,000 to 5,000. That's why I provided a non-zero value. I mean, you can't fly your aircraft when your altitude is zero. And please note, these are with respect to the Earth center, Earth fixed frame. So you can be at zero north, zero east, but you cannot be at zero down. Then it won't be a plane. It will be it won't be even a car. So, all right. Then what I want to do is, once that is done, at this point you have a choice. You can click on generate MATLAB script, and that will write a MATLAB code that will perform the trimming. So if you see my screen, it will actually create a code that will generate the trimming. Now the next part of this code, or this next part of this discussion, is linearization. So before I go to linearization, I just want to make sure that everyone got the operating point, trim operating point. Any question in trim point? Input, output, state? Any questions here? So for linearization, what you will do is model input output, operating point is OP trim 1, go down and hit linearize. And once you linearize, you are gonna get this information. That is the linearized model in state space. And please note, we have 4 inputs, 3 outputs. And what happened to the states? Initially, I had 12 states. Out of those, I have the linearization in 9 states. And the linearization is comprising less number of states, because the states after linearization, the derivative and the states are becoming zero. So if you look at the PQR, the state is zero, derivative is zero. So that dynamics is not affecting the overall performance of the aircraft. So Matlab did the minimal realization, and now your reduced order model is 9 states. If you go on to the transfer function, please note, you have 4 inputs, U1, U2, U3, and U4. So from U1 to Y1, this is the transfer function. From U1 to Y2, this is transfer function. U1 to Y3, this is the transfer function. And for U4, U2 to, so these are all the respective transfer functions. And it will give you also the inputs U1, U2, U3, U4, and the outputs Y1, Y2, Y3. So the next part, which is, if you look at your project, the last part is finding out the eigenvalues. So, and I'm gonna spend just 1 minute to discuss what this is. So what he's asking is, he wants you to find the eigenvalues of the A matrix corresponding to the linearization. So go to transfer function, go to state space. This is your A matrix. What I would do is I will copy this A matrix inside the Matlab and find the eigenvalues. So if you look at question 5.8, question 5.8. In project 4, you have to find eigenvalues of A. So you would copy this. If you want, you can actually try Lin Mode as well. You can also use Lin Mode. And that is the project all about. Unfortunately, I don't have time today to show you the joystick interface, but I'm going to stop here, and I will continue the discussion in next class. But